They will react with acids as well to make salts. We kept it pretty simple, but we did talk about the fact that you can take something like a nitrobenzene and you can reduce that to an amine using what reagents? I'm adding hydrogen. How do we know how to add hydrogen?
Is it the H2PV?
We can do that actually. You can use hydrogen gas and palladium.
Acid and iron?
That's right. So I told you we can do that,
It's expensive.
but it's expensive, right? And so another way to do it is to just use hydrochloric acid and iron. Right? So that's why I talked about, you know, you could literally go down to the hardware store and buy iron nails and chop them up, put it in there with a little hydrochloric acid, and you can do the same thing. So you can reduce those things. Chapter 11 was all the spectroscopy stuff, which we've already kind of talked about. I don't know, I can't remember 100% for sure, but I don't think I put any carbon NMR on it, so it's just pretty much a proton NMR and IR in terms of the spectroscopy. And then, of course, chapter 12 was where we were starting to talk about aldehydes and ketones. Don't forget, I didn't get around to doing the demonstration, but there's the Tollens reagent, which takes an aldehyde and converts it to a carboxylic acid ultimately, but also makes a silver mirror. So you get a silver mirror. It's a positive test for aldehydes that we do in chemistry. It makes nice shiny mirror flasks, and I will make a mirror flask for you when we get back.
Just for the perfect score people or for everyone now?
Well, I don't have enough money to buy them for make it for everybody. I will make, as I promised, I will make one for anybody who gets a perfect score. Everybody will get to see it be made. So that's what the Tollens reagent does. It's actually important in biochemistry because there's these sugars called reducing sugars that have different biology than non-reducing sugars, and so it's one way in which you can test for the presence of reducing sugars is to use a little bit of Tollens reagent, because a reducing sugar is actually in equilibrium with the aldehyde form of the sugar. There's another test that I forget that biochemists prefer over the Tollens, but it's the same kind of thing.
Did you say that we use this for determining if there's a...
This is for aldehyde. Yeah, this tells you if there's an aldehyde around. Ketones don't do this, just aldehydes.
Wait, I'm sorry, can you say that again? What, it tells you if there's an aldehyde around?
Yeah, if you had an unknown and you wanted to know whether or not it was an aldehyde, you could add a few drops of the Tollens reagent, shake it up, and see if you got a silver mirror on your test tube.
Can you just go over oxidation state real quick?
Sure. Yeah. So let's let's start off with carbon dioxide. Let's start off with the easy one. Right? The difference between oxidation state and formal charge is that we don't assume equal sharing of electrons. Right? Formal charge, we assumed everything shared equally, right? And so the formal charge of this carbon, right, is 4 minus what? For the formal charge.
Formal charge?
4 minus 4. Yeah, so it has a formal charge of 0, formal charge, but its oxidation state or oxidation number, right, comes in with 4, but we assign all of the electrons to the more electronegative atom, right? So how many does this carbon have? It doesn't have any of those, 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 so it's 0. So even though it has a formal charge of 0, it's in the oxidation state of plus 4. Right? Now, if I look at something like a ketone, and I want to know the oxidation state of that carbon, it comes in with 4, and then I subtract what it owns. How many of these does it own? None of those, and none of those, right? But it has half of each one of those because it's their other carbons, right? Mm-hmm. So that's in the plus 2 oxidation state. So remember, it's the difference in how you assign the electrons is the difference between formal charge and oxidation state.
And isn't this just like an easier way of doing the whole oil rig thing?
The whole what?
Oil rig, with an acronym, oil and rig.
Yeah, so oil rig, oxidation is loss, reduction is gain.
That's just a simpler way to do the same thing.
Well, oil rig was really about determining whether or not something was being oxidized or reduced.
Right.
So for example, if I did this reaction, and I asked you what's going on with this carbon, what would you tell me? Is that carbon being oxidized or reduced in that reaction?
The carbon?
What's that carbon that I dotted? So it started off as a ketone and became an alcohol.
Reduce?
It's being reduced, right? That's what oil rig is. But it's hard to see what gained electrons, right? Oxidation is loss of electrons, reduction is gain of electrons. So, but if you do the math, right, we just said that that has to be in the plus what oxidation state? Plus 2, right? And if we look at this, right, it doesn't get any of those. It gets one of those, and how many of those? What's more electronegative, carbon or hydrogen? Carbon, so it gets all 2, right? So it gets 2 of these, one of those, so 2 and 1 is?
3.
So it's in the plus 1 oxidation state. So how many electrons did it gain? It gained 1 electron in terms of,
So it doesn't get both the electrons from the hydrogen?
4.
2, oh yeah, 4, sorry. It's in the 0, so it gained 2 electrons, that's right. I heard somebody say 3, I think. What else?
Do we have to make any, like, do any reactions with a protecting group? Like, we have to make this, like, acetyl, whatever how you say it?
Acetal?
Yeah, that, and then you make the product, and then you remove. And then you
I didn't put anything on there where you would have to remove an acetal.
Okay.
So it would be fair game for me to have you put an acetal on something. But I'll just tell you, I didn't have you do the reverse on the example. So it's 25 questions. I will tell you that the bonus question is not multiple choice. You have to write something. And I will tell you that what it is there's boxes that you have to put the products in. So there's a starting material, a line, something, put a box, and then that has a line, kind of like what we did on the day that I had Thomas come in and pass out, where there was those boxes. So it's not that question, but it is a similar question. So you actually have to draw a few things. So I ask you to put your name on that page separately as well in case it gets torn apart. Yeah.
Oxidation of enzymes?
Oxidation of benzene, I didn't put anything on oxidation of benzene in there. Yeah.
Would you say it's like an even split with like questions that have like, let's say charts or reaction mechanisms versus questions that are just words or
I
math?
wouldn't say it's even split. I mean,
You say it's one or someone's
the fact that there's spectroscopy on there, there's probably fewer reaction mechanisms in terms of per question, or, at each question than there was on the previous exam. Because the spectroscopy questions aren't really reactions. So they take up I would say spectroscopy in some form or another is probably about a quarter of the exam.
Yeah, you said there's no Hooke's law either.
No Hooke's law. No.
Are there gonna be questions like wavelength, like is a microwave bigger than this and stuff like that? That was just like to help you understand.
No, that was for you to help you understand where things were coming
Because there was like, more like that.
But there is a problem where it's a couple of steps. There's a product, there's a thing that you can select from, and then there's, an NMR and or an IR. And so if you know the chemistry and you forgot the spectroscopy, you should be able to get the right answer. If you forgot the chemistry and you know the spectroscopy, you should be able to get the right answer. If you forgot both of them, sorry. What else?
Are we gonna have to determine like percentages of like trace or elements, like ortho, like what, those like ortho and parallel ones we have to do?
By the time I got around to thinking about ortho, meta, and para questions, I didn't have any
Okay.
space to put anything. So, all of your electrophilic aromatic substitution reactions are just monosubstitutions. So like starting with benzene, put one thing on there.
Okay.
Now, that doesn't mean that I might not use a name like paranitro whatever.
Yeah.
So you need to know what ortho, meta, and para are. But yeah, I don't think I gave one where you already had a substituent, you had to determine whether it was ortho, meta, and para. I should have, but I didn't.
Sorry.
And it's already printed out, so I'm not gonna change it. There's plenty of space on the exam for you to write. I encourage you to do so. I've put areas for you to write like I have always. But don't be afraid to. The exam will look thicker than it really is because spectra take up space, and I wanted to make them big enough for you all to see. And so there's a lot of the questions that are just single questions on a page because of, don't be freaked out by it being a little thicker than usual.
When looking at the IR spectra, are there any questions that are gonna have you, like, I know you said, of course identify it, but like identify multiple functional groups in one?
That's fair game, yeah.
Because there's some practice problems.
So for example, going back to the carboxylic acid question, right? A carboxylic, how would you distinguish a carboxylic acid from an alcohol? Well, you would look in the hydrogen region and in the sp2 region, right? You have to look at both, because an alcohol will give you a stretch and not have anything in the sp2, but a carboxylic acid would have the OH and the sp2, so.
There was a practice question that we were doing, and it was like, we had to determine, like, if it was an like, there was one question, it was like, it looked very similar to another question, but the difference was one was an aldehyde and one was a ketone, but both had like the,
Almost like the same,
This-
but like, I think the ketone had more
It could have more peaks, but the aldehyde will have that hydrogen that's attached to the carbon of the carbonyl, which is sp2, so it'll be shifted over a little bit. So you'll have all of your sp3 hydrogens around 2,900 or whatever, and then you'll have a little bit over from that, you'll have the aldehyde, which would probably be a small peak. I will say that all of the choices that you have are, in my opinion, pretty straightforward. So if you know your rough areas, I think you'll be able to answer the questions. There's not going to be anything in there where you have to get down to the exact wave number to figure out the two things. If you know the rough regions, you should be able to answer the question. Because some of them get kind of close, right? An aldehyde and ketone might shift a little bit, but the ranges overlap. So,
If you give us any splitting and stuff, it's gonna be like clear, right? Because some of the problems were like, they're so close together, like you can't really
yeah, I
tell.
focused on things that were very clear, in my opinion, very clear.
But when you put, sometimes on that board, there's multiplets up there, there's like 6, I can only see 4.
Yeah.
And I'm like, yeah.
They're all pretty clear, big and blown. I made sure that it was big and blown up so you could see whatever you needed to see. There can be a lot of detail in some of them, no doubt about that. But again, I tried to focus on the common stuff.
Is there anything on the test that we didn't kind of touch on? Like any specific topics that would be?
To the best of my recollection of putting the exam together, we talked about everything. Now, I'm not saying that I talked about it for 45 minutes. But everything that's on the exam, we have covered in class.
So no like curveballs or?
I don't think I threw any curveballs. But the curveball is relative to the batter, so you all know the batters. You know, I don't know. I think I'm throwing them straight over the plate. Having said that, you got to think. I mean, I'm asking questions that you have to think about, yeah, but I don't think I threw any curveballs.
Do you have a lot about nomenclature, or like naming them?
In fact, I mean, I could be wrong, but I don't think I put a single solitary nomenclature question.
I feel like we cover so many topics in this class, like nomenclature for each, like you can make a whole test on just that.
Yeah,
You could.
please don't.
I did.
It's too much rules for me.
Do you have a question? No? Awesome.
So you said it's mostly, well, we said it's a lot of like determining if they're aromatic or like just like determining. Like you said something like main.
I said there is quite a bit in terms of the reactions that have to do with aromatic. Yeah. So electrophilic aromatic substitution was an important thing that we covered. You know, we also talked a little bit about making aldehydes and ketones, so don't forget there's, you know, the oxidation of alcohols, right? So if you oxidize a primary alcohol, right, if I wanted to get an aldehyde from that, what reagent would I use? if I wanted to take a primary alcohol and make a aldehyde out of it, what oxidizing agent would I use?
Was it, like, there was a specific one and then it was like free oxygen, something like that, or like O2. Is that what you're talking about?
So if I have a primary alcohol and I want to make an aldehyde, what reagent would I use? 3 letters. Let's play hangman. First letter starts with P.
PCC?
PCC, yes. So PCC plus a primary alcohol gives an aldehyde. A primary alcohol plus Jones reagent gives a
Plus Jones.
Is this from chapter 8?
little bit, yeah.
Okay, because I've heard that before.
Yeah.
It's been a while.
Can we
You
write
wanna know
that?
what Jones reagent? I got it right
Jones reagent does what?
now. C-chromium, CR3.
So if I have primary alcohol and PCC, I get an aldehyde. If I have a primary alcohol and I use Jones reagent, I get a carboxylic acid.
Isn't that under harsher conditions?
It is, Jones? Yeah, it is harsher conditions, sure.
The higher temp?
No, it's just that it's in water and it's got a lot of acid in it. That's what I mean by harsher there.
This is in chapter 8, just so I know where it is.
I think so, yeah.
Yeah, it is.
So we
I thought so.
we didn't cover all of chapter 8 on the last exam.
Yeah.
So it's still fair.
I didn't remember that.
Right. And if I have secondary alcohols, either reagent will give me ketones, right? Both of them will oxidize that. Tertiary alcohols don't undergo oxidation, at least not to ketones or aldehydes.
And what is Jones reagent? Like, would you just say it's Jones reagent, or do you actually just give the?
So both are fair game. So Jones reagent is a mixture of chromium trioxide and sulfuric acid in water.
Say that again, chromium.
CrO3, sulfuric acid, and water. That is Jones reagent. PCC is pyridinium chlorochromate, and there's no acid or water around.
Okay, so the primary alcohols are oxidized to aldehydes with PCC, but they're oxidized to carboxylic acids with the Jones reagent.
That's correct, yep.
And what's the last one?
This one?
The OH?
That's a secondary alcohol. Either one of these can actually make a ketone from a secondary alcohol.
Oh, okay.
PCC or Jones reagent will both work equally well to make a ketone. It's the primary alcohol you got to be careful with because it can either give you an aldehyde or a carboxylic acid, depending on the reagent you use. Anything else?
Hello.
So reagents, that also, that does not limit to Greeners and Collins.
You need to know all the reagents that we've talked about.
So
Yeah.
like all those like FB.
Yep. All of the stuff that we use for electrophilic aromatic substitution, making Grignard reagents,
Yeah, I want to make sure.
sodium borohydride, lithium aluminum hydride, Jones reagent, PCC, all of those are
So we can
things that you need to know what they do. Yeah.
list.
What's that equation?
Which one?
The one, the entire thing?
Oh, so I'm showing the oxidation of a primary alcohol to an aldehyde, you need PCC. A primary alcohol to a carboxylic acid, you need Jones reagent. And that a secondary alcohol can be oxidized to a ketone with either PCC or Jones reagent.
So when we're doing the spectrum, so what ranges we go from for the spectromium, the spectrometer?
So what spectra are we going to look at?
Yeah.
So I told them earlier that I'm focusing on IR and proton NMR or hydrogen NMR. I've ignored carbon NMR for this test, to the best of my recollection.
And what ranges from 1,500?
Well, in the IR, we start at 1,500, and then we draw a line at 2,000, and then we draw a line at 2,500, yes.
Earlier, did you say when we're like trying to discern when there's something aromatic that we just assume it's planar if we're given a bunch of choices? And,
Yeah, assume it's plain. But know all four rules for something to be aromatic. Everything has to be satisfied, right? It has to be plain, it has to be cyclic, it has to be conjugated, and it has to satisfy Hubble's rule.
All right, so when we're doing the hydrogen, we have to make sure that it is, so if it's the same on each side, it only counts for, like, 1, 2 counts for the same, right?
I'm not sure I know what you're talking about.
Am I right on the board?
Yeah, you can run with it.
So, for example, if we had this,
Okay, so you're talking about like symmetry.
yeah,
All right, so are you talking about the number of signals?
number of hydrogens.
Well, the number of hydrogens is going to be the number of hydrogens, right? So let's look at an example. So we looked at this earlier where we had something that was like this, right? The number of hydrogens is 3, 4, 5, 6, 7. It's got 7 hydrogens. But how many signals we will see, right? We've got the symmetry through here. So this is going to be a signal, this is going to be a signal, and that's going to be a signal. So there's going to be 3 signals because of the, so there's going to be 3 signals but 7 hydrogens overall for that molecule.
So why is it 7?
Let me draw them in for you. There's 3 hydrogens there, 1, 2, 3, and 4 hydrogens on the rings.
Okay.
So the total number of hydrogens for that molecule is 7. But the number of NMR signals that you will see will be 3, right? And so if we tried to, now you're not going to have to do this on the exam, but I'm just giving you an example. So if we were to look at the NMR or predict what that NMR would look like, we would start at 5, right? Where would the CH3 be? Would it be on this side or would it be on this side?
It'll be on this side.
Yeah, it'd be upfield, right, of 5, right? It's going to be somewhere, let's just put it at around 2, and it's going to be a singlet. Why is it going to be a singlet?
Because it's all together.
Okay, what do you mean by that?
Well,
What do we use, what's the rule for splitting?
Neighbor.
The number of neighboring hydrogens, N plus 1, right? These three give one signal. Does it have any neighbors? No. So it's going to be a singlet, right? These are going to appear on this side of 5 because they're all these hydrogens are attached to an sp2 hybridized carbon, right? So I'm going to have a signal for this group, and I'm going to have a signal for this group. Okay? Now, how many neighbors does that hydrogen have?
1,
1. So it's going to be a
doublet,
doublet. How many does that hydrogen have?
1,
And so it's going to be a
doublet,
doublet. Now, is it going to be further downfield or further upfield from this one? Yes.
Down.
Why?
the oxygen, the nitrogen.
That's right. So it would look something like, that would be what that NMR would kind of look like. And let's just label A, B, and C. A, B, and C. And the integration would be 1 to 1 to 1.5 would be the relative number.
You talked about, you talked about chapter 9 yet?
Have I what?
Talked about chapter 9?
Oh, yeah.
I woke up late.
That's okay, you can watch it on the video. I'll upload it. But yeah,
Have you gone over 10 yet?
yep, we've covered everything. You can ask any question you want to ask, but you can also watch the just general overview on the video.
I had things coming up tonight.
It's okay. That's why we record. I'll get it uploaded as soon as I can. You are not going to have to do that on an exam where I'm asking you to draw an MR, okay?
But do we have one where we have to look at one?
Oh, yeah. You'll have to look at an NMR and determine which molecule it represents.
All right, so I understand that one. So B is that way because it's bound to a column.
Yeah.
And the reason I was asking about symmetry is because those two H's on the left side, on the right hand side, match those.
Yeah.
Okay.
This is B, and so is this,
Okay.
because of symmetry.
Okay.
Yeah. So I would recommend you all have, have your model kit ready to go, have some pieces put together. Be a good idea to have a carbonyl put together.
What will
So-
we need the model kit for?
Well, to me, it is helpful sometimes to build a model in terms of determining the number of signals. I can actually hold the model in my hand.
Oh, you're talking about if you write it out as like the formula,
Mhm.
instead of actually drawing the structure?
Yeah.
Oh, okay.
So for some of you, that might be more helpful to actually look at the model as opposed to looking at it on the paper. So that's very important.
Or of course, we can just draw it out too, right?
You can, whatever works for you.
So how would you find aromia?
Pardon?
Aromatic?
Aromatic?
Yeah, that one.
Okay, what about aromatic?
How do we find
So you have to apply the 4 rules, right?
planetary?
Is it planar?
Does it have bonds?
Well, they all have bonds, but you got to be a little more specific than that, right? So it's got to be planar,
Planar,
it's got to be cyclic.
which is the vast.
Yeah, the ring, right? And it has to be conjugated.
Country, what does that mean?
So conjugated, if you were to look at something like benzene, every carbon atom has a p orbital on it.
Oh, okay.
But the way that I always think about it, it goes double bond, single bond, double bond, single bond, double bond, single bond.
So conjugate means basically double bonds.
It means double bonds in that arrangement of double, single, double, all the way around the ring.
Okay, what's the fourth rule?
You tell me? It's a person's name.
Heckler's rule.
Huckel's rule, yeah, what is that?
It said number of electrons 4 equals plus 2.
Close. The number of pi electrons is 4 times n plus 2.
That's equal to 6.
Doesn't have to equal 6. 6 could satisfy that. All right, so you put the number of pi electrons, so for benzene, it is 6. So 6 is equal to 4n plus 2. So 4n is equal to 4, so n is equal to 1. Huckel's rule says that n must be a whole number, including 0. So benzene, it is planar, it is cyclic, it is conjugated, and it satisfies Huckel's rule. It is an aromatic ring.
We're going to throw my question at the top of my head.
Okay. Anybody else have any questions? I can't help you with your writing. Have trouble with mine?
It's not my handwriting, it should look like a catalyst. What reaction it is, I guess. It's just a reduction.
All right, folks. See you bright and early in the morning.
Yeah, did you grab it all? Did you grab a chapter 12 homework yet?
No, so I have not graded your chapter 12 quiz yet.
Okay.
So, since we handed in that thing for, that worksheet for chapter 12 quiz, is the next quiz gonna be chapter 12 or chapter 13?
Next quiz will be chapter 13. So for those of you who were in class and did the homework thing, I took that up as your quiz. Those of you who had an excused absence, I asked you to turn in a problem from chapter 12.
Yeah, I sent you in my excuse.
You sent it, yeah?
I was telling the truth.
No, that's fine.
I told you she had